So in the last lecture, I described reducing the problem of factorization to a problem which is finding a period of a particular function. It required lots of results from number theory, various identities that have been known for many centuries, and it's a kind of a somewhat of a elaborate exercise, but there is nothing fancy involved in the whole analysis. And what it achieved is the reduction, which can be labeled as certain complexity. So reduction of factorization so it requires two ingredients, which is calculation of the greatest common divisor done by Euclid's algorithm, and assuming that it is very easy to check whether the number is a power of a prime number or not. And the greatest common divisor, I explicitly proved that the complexity is log n cube. You can put order notation. This I explicitly showed using Euclid's algorithm that it goes as the third power. So n is a number to be factorized. And the outline of how you can check for a prime power, it is given in the book by Nielsen and Chuang if you want to look it up. Not too complicated, but I will not go into too much detail about it. It's enough to know that both of them are order log n cube. Log n, as I described last time, is the number of bits required to encode the number that you want to factorize. There is actually another result. That can tell you whether a number is prime or not. The factorization is something more. It says that find the factors afterward. But if it is prime, that says that there are no other factors, but you don't know anything more than that. If it is not prime, you don't know what the factors are. So this turns out to be another algorithm which is a polynomial in the same number of bits, 2 raised to some power, and people are still trying to make this power as small as possible. And the interesting part of it is that this proof that it goes like power of the number of bits was provided for the first time by Manindra Agarwal and his students at IIT Kanpur. After many centuries of people trying to find it, they came up with a simple looking algorithm but completely different type of analysis. So that is a interesting bit of history, and it was discovered maybe 20 years back. much after all the quantum stuff started. So anyway, what they showed was that they first gave a proof that this number is 12, then some other identities reduced that number to 8, then afterward this number was reduced to 6, and people are still trying whether it can be reduced further or not. So this is a side story, but it is also something which can be done. And all are the powers of number of bits.
This relation in the power. This relation in the power.
Yeah, S is this power.
Like, is it the same computation model? Different algorithms are being prepared, or?
People found out various other tricks and improved the algorithm.
No.
Yeah.
So the computation model is
Same.
same.
Yeah.
The complexity class.
So original proof was little more elaborate. People simplified it, reduced the power by using all kind of tricks. There are all what you call vast number of results in number theory. Okay, so depending on what identity you use in which particular place, you can modify things here and there. Okay, so this is the background that yes, we did this. Now comes the question is finding a way to get the period. And we know, again, nothing to do with quantum physics. It has been long known that if a function is periodic, using a Fourier transform does a very good job. Okay. So now we'll ask what a Fourier transform can do for a periodic function. Assume that the and yeah, this whole stuff, whatever it is, they are all probabilistic. So it's not a one-shot algorithm, deterministic situation, but the probability is reasonably large, so you don't worry about if you don't succeed once, you try it 2 times, 3 times, and it will get there. That is not a problem. So what does Fourier transform do? And here, again, a lot of stuff is known in the classical framework. So I'm not going to directly jump into the quantum stuff right now, but use the classical description in the quantum notation. That's all, because then I convert one to another thing, change will not be too complicated. So Fourier transform is a unitary operation the norm of the state doesn't change. It's a well-known identity, or if you remember the formula, it will have a phase, and the inverse is thus defined by changing the sign of the phase. The whole structure looks the same. So nothing is going to get complicated. The changing the sign can be interpreted as a what you call Hermitian conjugate operation. So it's a unitary structure, and that makes life easy when you want to convert it to quantum language. Unitary operators are all over the place. The second thing is it's a linear, well, it's a linear operation, so the sum of Fourier transform of 2 objects is sum of individual one, and which will help us when we want to do superposition. Okay. Classically, you can't do superposition, but in quantum theory you can, and that's not a complicated situation either. And I will describe the process that the whole transformation can be factorized. This is an important ingredient in simplifying any algorithm in classical case. If you have a complicated function, you can factorize, the number of operations comes down. And it turns out that this can be factorized completely in terms of the smallest possible ingredients. So now I will write down that it takes for n values are transformed by an n by n matrix. You can write all these things very trivially. That is what is true in general, and you have to go along with a particular notation. But the point is that I want to clarify that this n right now is kept separate from what this n is. Even though I'm using the same notation, I will use a completely binary situation where this is 2 raised to n. This number to be factorized is always an odd number. Even number is too simple. But I will write it in this particular notation, and then we'll worry about what happens when I want to convert this to any arbitrary number. There are small modifications, but things don't change any drastic manner. So now let me write down the notation that Fourier transform takes these values f of x for some function. I'm going to use quantum notation, so every value of x is associated with some basis vector, some direction in the classical space, and the whole function is defined by the set of all values of x. In particular, x will be this equal to a set of size capital N or equivalent to size 2 raised to n. What does the Fourier transform do? Is it changes the function from the argument being x to argument being conjugate variable, which I will call y. So this is convenient is 0 to 2 raised to n minus 1. Then another set of values will have the same range to maintain the normalization. This factor 1 over root n is inserted. It is part of the classical description only, and it is square root of n because when you do the second times apply the Fourier transform and its inverse, everything will be normalized properly. The numbers will look the same, and then I have to now write down the conjugate expression, which is well, this sum over x is still there. Then e raised to 2 pi I x y by n. This is a phase which I have chosen in a particular convention. The reason for this choice is I am treating the function in a range of variables going from 0 to this capital N minus 1, and this phase enforces modulo n operation. Because what happens when you take two numbers and divide by n, there is an integer part and there is a fractional part. The integer part, because of e raised to 2 pi I, doesn't contribute. What remains is the fractional part, which provides the phase. So it's just a convention, but because we are going to use all the time modulo n operation, it's nice to put this 2 pi I outside, so then x, y, everything is a standard set of integers, and then the basis changes. It was x here, now it's the basis y, and this bunch which is sitting inside is a Fourier transform of the function f of x. That is how the definition goes. If you have a function f of x multiplied by this particular phase, sum over all the values of x, and whatever you will get will be the Fourier transform. You can call it f tilde of x if you want, but that's same thing. And as I said, because it's a unitary operation, if you want to calculate the inverse, all you have to do is flip the sign. Nothing else. Everything else remains the same. So inverse this 2 pi I goes to minus 2 pi I. That's all. Now you will use all the tricks of simple algebra, linear algebra if you want to say so, to simplify this phase. Okay. Because there are some numbers, etc., in some particular range. So let me write this in a binary notation. So it goes from 0 to 2 to the power n minus 1. So it will be described by a whole bunch of digits or bits, and I will write them in some sequence. So the largest one is I will call xn minus 1 times 2 raised to n minus 1. The next one will be xn minus 2 raised to n minus 2, all the way it goes to x1 times 2 plus x0. This is just a place value system. The first bit, it's multiplied by 1, the second by 2, 2 to the square, 2 to the cube, whatever it is. And I can write the same thing for y. And now I ask the question, what is xy divided by n fractional part? So that is what is sitting here. Integer is out. So you can now imagine, I will just multiply this whole expression, n terms here, another n terms over there, and there will be lots of contributions in their order n square if you want. But out of that lot of contribution will have a power which is greater than 2 to the power small n. For example, if I multiply by this, it will be 2 raised to 2n minus 2, that is going to be larger than 2 raised to n, it will contribute to the integer, but it's not going to contribute the fraction. So I have to now I can look at it term by term. Which of this particular term will contribute to the fraction? That means in the product, the powers of 2 which multiply should not go bigger than 2 raised to n. So if I look at the first term, I just this xn minus 1. The only term which can contribute is y0. Okay, and what will be its power? It will be 2 raised to n minus 1 by n. Any term here will when multiplied by well, I'm just looking at the first term here, so x will have this. Any other, if I take y1, it will become 2 raised to n, and then that becomes an integer. No good.
It's not y minus 1.
Huh?
It's not y minus 1.
Yeah, so I can continue all these things. The next one, xn minus 2. Then there will be 2 terms which will contribute. So it will be y1 times 2 plus y0 times 2 raised to n minus 2 divided by n. And it can go further. So the first one, xn minus 1 will generate only 1, xn minus 2 will generate 2, 3, etc. But now this can be written in a convenient form. What is this x coefficient of x minus 1? I will write it at y0 multiplied by half. That is a fraction written using this binary point, which is generalization of the decimal point, but that is what it is. What happens to the next one? This stuff divided by 4, this is get a term which is half. This is the next one which is multiplied by 1/4. So now this is a very nice structure. Okay, this is what you can call it a binary point. The simplification is that x and y dependence is completely separated. That is what you need for factorization. If I look at xn minus 1, it will appear in only one particular contribution to this, which is given by this particular factor and nothing else. So I can write this as a bit by bit structure, just exponentiating all these things which are independent. You just write them separately, and that allows me to perform this sum. Because what is this sum? I have to sum for xn minus 1 taking 2 values, xn minus 2 taking 2 values, etc., etc. Here it is just a linear term, so I just sum over to 2 terms. Nothing complicated. And so now I will write this stuff. And yeah, let me leave out this for the time being and reorder the things a little bit, which makes life easy. So it's avoid writing too many things. So this stuff can be interpreted as a superposition with this coefficient f of x, and I don't want to carry out all the superposition coefficients separately. I will write just basis vector, and then I can perform superposition with whatever coefficient I want. So you just look at this transform. So if I know this basis vector, how they transform, I will perform the superposition afterwards. So that allows me to avoid writing this summation all over the time with some coefficient f of x. And all I need to do is this x is a summation over y and that now becomes easy to construct by just explicitly writing out all the summations one by one, because this x and y kind of separated. So I can write it as what is a term which is xn minus 1. So it will have two contribution depending on this y0, which I am summing over. So it will, and there is a root n somewhere. What happens when y0 equal to 0? The phase is not there, and when it is there, it is e raised to 2 pi I x n minus 1, y0 is equal to 1. So this is the contribution of the first term, coefficient of x to the power n minus 1. As I said, it's in the exponents. I will write down this, everything separately, no problem. So that becomes just ordinary factors. Then what is the, so this is the n minus 1 bit of this expression, which is xn minus 1. Then the next will be n minus 2 bit of it's x. I don't know to write. What it will contribute is 2 pi I. If xn minus 2 is equal to 0, it doesn't contribute anything. But if it is equal to 1, then there will be a contribution. So this stuff will, let me get the notation right. Well, I'm summing over y, so okay. I think I can flip the notation. It doesn't matter. You can write it either in this way or interchange x and y and write it in another way. That both those expressions are identical, and I'm summing over y. So actually, this is I can rewrite it as equally valid It's symmetric, whatever it is.
Both the sum split.
Hmm?
Aren't both the sum split? Like, because like for the first 2 bits to n minus 1 by n term.
Both are present, but one of them I am interpreting as a superposition. Okay, this is the basis vector. These are all the superposition. I will postpone writing the superposition. It's unnecessary. I will write it for the basis vectors, and then I can perform sum over x for superposition. That leaves only the phase, which is easier to write down. Okay, so I can use either of the two expressions, no problem. This is completely symmetric, and here I'm summing over y, so it is kind of easier to write it as this particular, the second notation. And this is not x, this is y. All of the y bits are summed over 1 by 1. So the first one is only contributes here, and its exponent is this. It will contribute only when the y is equal to 1. If it is 0, nothing will happen. If it is this one, this n minus 2 bit, again 0, nothing will happen. But when it is present, I have this number sitting inside. And there are n factors. So what happened here? There are n terms in the summation. This was 2 raised to small n, and now I have small n factors. Each one of has 2 terms. So it does the same job. But the point is the whole thing got factorized. And I will ask, I have to calculate this, well, I have to do capital N terms of summations. How much effort will be required to do this? Well, I have one summation inside each factor, and then number of factors minus 1 if you want to do many multiplications. So suddenly the operators which is here came down to this. Okay. And that is a tremendous advantage, because difference between here to here is exponential. So now I can ask that I have to do the full function, is a superposition. So the full function is superposition of all these basis vectors, and computational requirement is order and square. You can look at it in many different ways. What I did was just look at these n terms, and then there are capital N number of these individual components. I want to calculate the whole set. So one n times another is order n square. Or if you directly want to look at in this matrix representation, you have a capital N cross n matrix. You want to multiply by n component vector. How much effort will be required? So I multiply by first row and the column. Well, there are n operations. I have to keep on doing for every row. So n times O, it becomes order n squared. So this is without any trick, but after factorization, all these things, the computational is order n log n. And that is the advantage of doing this. And this is a well-known algorithm available or known before quantum mechanics came along. It is a more commonly known only by its acronym called FFT, stands for fast Fourier. And linear algebra library is available on most computers, will automatically contain this routine. It's just known by FFT, fast Fourier transform. What it does is it gives this particular simplification. And it is completely describable using classical concept of factorization. The only thing I have done is use the quantum notation, but that doesn't matter anything at this particular stage. So now the question is, what will be needed to get quantum advantage? So quantum advantage, as I have said many times, comes from being able to use the superposition cleverly. So classically, each f of x is handled independently. That you will calculate for one value of x, then another value of x, etc., etc. The quantum trick but this is not enough. That yes, you can do a superposition. We have seen many examples of superposition where yes, you have a collection of all the components together, but then there is a catch. Yes, you have all of them together, you want to measure. Then you can measure only one. As soon as you get one answer, everything else becomes zero. So somehow there is a large number of superposition here that can help when these are n components of f of x can be converted to only Because at the end you are going to have small n number of bits, and those are the only thing you can measure. So this is the catch, that yes, you can do superposition, but you must find a way to collapse this large number of components to only a reduced number of measurements. If you are able to do that, then you have achieved something non-trivial. Okay. And that requires, so you run the algorithm once with all this superposition, and instead of running it for each individual value of f of x, and only perform n measurements. Then the effort, computational requirement, is smaller, because this one factor of capital N is going to go away. You are not going to evaluate all the components. You are going to evaluate only one superposed states, and you have to perform ultimately a small n number of measurement. So that requires this 1 of the n will again get converted to log n, and then the total requirement becomes log n squared. But this is a crucial point. How do I collapse? And this fast Fourier transform does not have any answer. We have to figure out something extra. And that is the part which Shor figured out how to do it. It went into all analysis of number theory to fill in all kind of gaps, because that is still required when you do this particular collapse. There are still more tricks needed to say that yes, I can get the requested answer, but this is what we are aiming for. Okay. So I'm going to use this fast Fourier transform as an operation, but only once. And then I'm going to perform a measurement. Can I extract from that measurement what is the period? Okay. Classically, I will have to do it for all the components to be able to extract the period. Here is something required which is extra. So now I can fill in various gaps, but what happens when you try to perform this Fourier transform in a quantum circuit, when you can do the superposition, and how you will be able to reduce the effort. So the first job is to just write this factorized version as a quantum circuit, and I will save effort by just doing it for 3 bits. That is a kind of caveat, but yes, I don't want to draw big pictures. 3 are non-trivial enough to give me the result. So for that I need to write this non-trivial part. 0 and 1 is a kind of a simple enough, but the phase can be non-trivial. So the first part is actually simple. So let us look at what this particular term does. I started out with some initial value and generated this particular thing as a superposition. So the first first factor, let me say. What is this expression? I start with 0 and 1. Don't do anything to the 0, but multiply the 1 by this particular component, and you can ask what is the structure. And I will take this 1 by capital root n as 1 by root 2 for every factor. That is just a trivial part. So you can write down this particular operation, and you will quickly realize that matrix which produces is this x0 with a decimal point is half x0. So this will give it e raised to pi I x0. E raised to pi I is nothing but -1. And if x0 is 1, you get a minus sign. If x0 is equal to 0, you don't get anything else. And this is a matrix which we have used very often, the Hadamard gate. And in that sense, the Hadamard operator is nothing but Fourier transform with capital N equal to 2. Just if n equal to 2, then you can just take the first factor and nothing but more than that. So this is well-known factor, and we know how to apply it to any particular state, no problem. Okay, any bit you take, you apply a Hadamard transformation, and the thing will give you the result. The next stuff now will become more complicated, and so I will define an auxiliary matrix which used what is known as phase in a particular sense. So let me give a notation R RD. And D minus 1 or D, that's okay. So here it is e raised to 2 pi I, but divided by power of 2 raised to d, and R0 is nothing but the third polymatrix, that this thing is equal to -1. Okay. What I need is something which can be called control RD, which is d actually is going to be the distance between qubits. I'll have to draw the circuit, then you will see this particular structure. So this will just look like this is a control bit, and then the target bit, this particular structure will be applied. Okay. So now the circuit for constructing this operator, and let me stick to a particular sequence. X2, X1, x0 and then how many brackets I need to add? Okay. This doesn't mean it's a jump, whatever it is, it goes across. And then need a longer line. I have to put it properly. So H okay. So this is a circuit, and now we can look at the various factors. So the bottom line is actually the first factor over here. All I have to do is apply this Hadamard gate, and that is what is applied, and it produces the leftmost factors over here, which happens to be the largest bit of y. So there is a important feature here, that the order of x bits is reversed with respect to the order of the y bits. Okay, so this happens automatically in that first thing. Now look at the second factor. If I apply h, then it will construct 0 plus 1 by root 2. And it will take care of the first bit, because that has exactly the structure buried in that. But what about the second part here, that I need a extra part of 2 pi I dot with x0, and that I am applying as a control here, because it will act only when x0 is non-zero, and it will apply this particular phase, which is exactly what is defined over here, and that is this R1. The next factor will have 2 pi I x2, x1, x0. The x2 is automatically taken care of by the Hadamard, but this x1 and x0 come with different factors. So x1 is just like over here, you apply R1 from the control, and x0 has to be applied with again a control, but the phase is smaller because x0 is now in the third bit position, so I have to apply e raised to I 2 pi I by 4. So I defined this notation, and then what happened here is that d turns out to be the distance between the qubits. This is 1 unit, this is 2 units, And that is just because this every time it moves by a factor of 2, the phase will drop by a factor of 2 as well. So this is the quantum circuit which will implement this transformation. And as I said, the full stuff will require that I do some superposition over here, and then some superposition of that will come out at the other end. That is fine, but the operations are all buried inside here. And now you have to ask how easily I can construct these various operations. So the Hadamard thing we have seen many times. You can construct by just a simple rotation, and that is given by the identity that what I call R0. Sigma 3 is something which can be also written as a Fourier transform here, but in more language of the just 2 by 2 unitary operation, you rotate the basis by 45 degrees. That is what the Hadamard operator does in the block sphere notation, and this is z-axis, this is x-axis. You rotate it, you go from one notation to another. And sigma 1 is an operator which we are familiar with in many circuits. It represents the operation of not classically. So you can rewrite now this thing as a different version. So I can rewrite as a sequence of such multiplications, whatever the number of times the whole stuff appears. So I can write this particular expression that I take h r d h multiplied by 2 raised to d times. The simple thing. The whole thing simplifies because h square equal to 1, identity. So at the end I will have just h r raised to d times 2 raised to d and another factor at the edge. And r raised to d multiplied by 2 raised to d is or there has to be d minus 1 somewhere, but that can be fixed without too much trouble. That I've defined something with a little bit of a mistake. Yeah, this has to be changed, that it is d equal to 0 is sitting over here, and this better, since it's a distance, there is a factor of 2 removed, so it's when d equal to 0, this is equal to minus 1, and that will satisfy this particular definition. The convention of what do you mean everywhere, d or d minus 1. So that is equal to so this expression which I need many times, h r d h, is actually 2 raised to dth root of naught. And this not is available in the classical logic, but keep on taking square root, and those things are exclusively available only in quantum logic. But the point is that you can do this without too much trouble, because this identity can be used to convert this control up with sigma 3 to control with respect to naught and taking some roots. But ultimately, if you just want to directly implement this particular rotation matrix, you can do it in any scheme. This is just something which can be identified without too much trouble, and that shows that it's not too complicated to implement it if you want to do it by some physical hardware. They are just going to be achieved as roots. This not this, but the control R. You want to convert from control RD to control naught. Well, you have to take certain number of roots if you want to do it that way. But there are many other ways of doing it. In practical hardware, one never really does this particular job. And there is another feature which is obvious inside here, that it is symmetric. Between the qubits. But the only term which is non-trivial are both the indices equal to 1, otherwise it is diagonal. You interchange the 2 bits, nothing happens. And that means that I can apply it either way, no difference, as far as this particular transformation is concerned. So the circuit can be rearranged if you feel like it. So that is one option which is available. And the other thing is one can truncate it, that this 2 raised to d is in the denominator. It's going to give higher and higher decimal points. And if I say that I want only so many decimal points in the answer, that is enough for my error criterion. So then higher decimal points, you can just truncate it. So truncation is possible. So if keep only up to distance d, or rather let me call it m, to get epsilon error, is 2 raised to minus m. So all these tricks are available, and in practical implementation, you can use this kind of tricks. But one can put this aside and just look at what this circuit requires. So how many gates are needed? So n Hadamard gates. How many of this thing is needed? Well, it's half of the full matrix, a triangular one, and can count how many of these control things will be there, and it's just the number of pairs on one side to the other part, which is n times n minus 1 by 2. So where n equal to 3, there are 3 of these control RD gates. Basically, it's an expression which is quadratic in the number of bits, but nothing more than that. If you want to truncate it, so anything larger than certain distance is removed, then it becomes n times m. But this is kind of good enough, and what we want is that number should depend basically no worse than quadratic in terms of these gates, and that is what we are looking after. That algorithm, we are just going to use it once. How much is the effort? It's nothing worse than log n square. So that is well, the first part of the story. We mapped it into a process and counted how many gates are there, and if you truncate it, it can be made less. There are all kinds of tricks that if you are just going to do this and measure the output directly after applying this transformation, then you can do all the rearrangement to an advantage by flipping all this thing in the other order. This becomes control, this is R1, this becomes control, R2, etc. And so all those things are controlled. The only transformation H, I will just measure Y0. And it will give me some answer, so I will measure it just after this particular stage. And depending on Y0, then I will act on R1 here and R2 here, because now once I have measured, I know the value. And that works throughout, that I can determine Y0. Now there are 2 of them. I will apply this connection of Y0 to both of them. Then I will measure Y1 at this particular stage. And then depending on the value of Y1, I can act on this particular thing. So that is if Y is to be immediately measured, the effort is actually becomes even less, because I determine it just sequentially. Because all these rotations kind of simplify. Once I measure y0, I know only how to determine one rotation and apply it to all the other bits. When I measure y1, I have to determine one rotation and apply it to all the following one, etc. And that can be cut down more. But most of the time, this is an uninteresting remark because we are not going to do it in the actual algorithm. But it can be done if you find some other applications. Okay. So now comes the question that I have to rearrange this stuff so that this algorithm use, but I only want capital N measurements, and I want to use that for determining the period of the function. So that is done for particular functions which we constructed, and the technique, which is again classical, is known as modular exponentiation. So what was our function? The function was defined with the powers, that is what we constructed. And I will write it in a quantum notation, so let me write it as a unitary operator acting on some particular state, and that has to produce A multiplying the argument x. So it basically does the job, but we assume that A and N are co-prime. And every time I apply it, it gives a power, because the function was defined as such. That is the periodicity which we have to calculated. So I write this thing in a unitary notation, where every time I apply it to a state x, it will multiply the value of x by a constant. And then I have to generate this by taking repeated application. Every time it will keep on multiplying by 1 power of a. So next time I apply this thing, it will produce higher power of m. We need lots of different powers for finding the period. So the notation may be a little bit confusing, but the x over here has nothing to do with x. It is just a description of basis. But the function which you wanted was a power function. And how are you going to generate it? Well, you can generate it by writing it as a unitary operator, which does this particular job, the notation. So now we need to calculate this operator u to some arbitrary power. Okay. And how does it done? It's again, we take advantage of this binary scheme. that I will write this in the same notation. M is some power m n minus 1 times that same binary decomposition which I wrote down, m0, and then ua raised to m can be written as some order. So with a 2 raised to 0 here, which is equal to 1. So what I do is I calculate all this UA, UA square, UA4, UA8, etc. in advance by repeated squaring, and then select which one I need for every value of m. So there are, so there's all the repeated square are constructed in advance. How many of them you need? Well, n of them. And the corresponding, then this whatever UA m can be constructed by control operation using bits of m. So I want to calculate all those things. Depending on the value of m, that particular bit, this factor will be present or absent, which is nothing but the control operation. So I construct this whole sequence once for completeness in advance, so many factors of them, and out of these particular factors I choose which one I need to complete this particular product, which is a control operation. And then I can construct this arbitrary power of m. How much effort? Well, this construction requires n of these powers in advance, and then multiplication using this control require another power of n of this control operation. It is completely okay. It's polynomial in the number of bits. And this strategy, this is called modular exponentiation. It is a classical in its construction, but I am writing it in again a notation with these unitary matrices, because in the quantum language that is how it will appear. But the way this is used now in this particular algorithm with this Fourier transform is kind of clever, and that is called now known as the phase estimation algorithm. It was actually discovered independently by Kitaev, and there is a story that Kitaev was in Russia. Shor announced his algorithm in the US, and Kitaev in those days heard it by some email exchange, etc., that well, the problem is solved and it uses Fourier Transform. But he didn't have any other detailed knowledge or the proof of the theorem or the copy of a paper or nothing like that. So he was clever enough that he worked backwards. I have to use Fourier Transform, and how will I solve it? And the technique he came up with is called phase estimation. It is not the same technique which was there in Shor's algorithm, but doesn't matter. This one is kind of more powerful, and nowadays its description uses this phase estimation language. It can be applied to this Fourier transform problem, but it can be applied to many other scenarios as well. Okay. So what is the problem? The problem can be faced very simply, that you are given this matrix U, and the given is eigenvector U as well. Find the corresponding eigenvalue. So first side you can say, what is the big deal? I know the matrix, I know the eigenvector, all I have to do is multiply them. And then whatever factor I will get, that's the eigenvalue. That's correct. The only thing is these matrices are of size capital N. So if you are going to multiply it, the effort is capital N. Multiply each row one by one and check that it works. So one row vector effort is N, second row another factor N. It becomes a usual thing, order N square. I don't want to put in that effort. I want to find the eigenvalue with order which is, this is a small n. And then one has to now play various kind of tricks which is available in the quantum language, and I can say that, well, I will write this phi as usual stuff. It is 2 pi I is already factored out, and what I have been writing with some number of bits. I was writing this n, and let me call this j here. So this is j bit precision. But I want to calculate this eigenvalue with some precision, and this is described by this set of bits. So fine. How do I do it? Well, we will combine these things with modular exponentiation, and I have to write the circuit. So let me do that. So I will write some number of bits. There are j of them. I'm just going to leave out everything in the middle, and then there is a Okay, let me put the dashed line a little bit over here. The eigenvector is given in some register U. And I'm going to use this modular exponentiation. So the first bit applies operator U. The second bit applies U square, etc. And the last one will apply the highest power which I need, which is U raised to 2 to the power j minus 1. It's a repeated squaring, starting with 2 raised to 0, which is equal to 1, then 2 raised to 1, 2 raised to 3, all the way to 2 raised to power j minus 1. And these are simple control operations which are available, but now I need the superposition, and there I will insert the usual trick. That apply the Hadamard operator on every bit, performs a uniform superposition. So this is what we have used many times. And now ask what is the final result. Not very complicated to write down. This is a action of U on an eigenvector. It is going to just put a multiplicative factor and nothing else. So final result I can keep as U and shift the phase, whatever came, onto the other line. It's a control operation, I can do it either way. And so the result is 0 plus e raised to 2 pi I phi times 1 by root 2. The next one will be 0 plus e raised to 2 pi I times 2 phi times 1 times 1 by root 2. Why 2 phi? Because now the operator is U square. And so how many times I apply? Well, I apply twice. And this continues that 0 plus e raised to 2 pi I 2 to the power j minus 1 phi times 1 by root 2. Nothing complicated, it's an eigenvector. Whatever phase is coming out with 1, I put it over there. Whatever power of U is there, it produces this particular phase. Whenever the control is 1, the phase will be there. The control is 0, nothing is happening over here. So you have this whole structure. It's a complicated state combining all those factors together, which will give a large superposition, but that is fine. And now I look at this particular structure. What is this 2 pi I times this particular value? So I have to throw out the integer part. Keep only the fractional part. That is what I did over here. And I can write it in different manner. Actually, I think I flipped the notation over here, and that can be little problematic, but that, yeah. The 0 was the rightmost bit of the expansion, so let me correct that to make it consistent with the way I was writing over there, that this is j minus 1 going to all the way to 0. Yeah, avoids confusion. So then this particular combination, okay, multiplying by all these factors, it produces various kind of thing. And let me start now at the other order over here. So it is 2 raised to j minus 1 times 5. What is this particular value where I multiply by all the powers of 2 and throw out the integer because it doesn't matter, and this basically produces just 0.50. Take all this higher power, shift it to the rightmost place, and that is what I get as the result. And the same thing. Take a lower power, it will keep the last so many bits. So all I need to do is replace this stuff by the corresponding phases. And that gives a notation which is there is 1 by root 2 . So this set is equivalent to the sequence. I just threw away all the integer part. Nothing more complicated than, and it produces this result. That is what the state is. It's a product of all the factors, whatever it is, because of all connection, but that is what it is. And then here is the final step. You look at these factors and look at what was achieved over here. Exactly the same. So apply inverse. This Fourier transform produced this result. Here you have that particular expression. You go back from here to the other side. And that solves the problem. So just to summarize, what we did was we calculated all these multiple powers by modular exponentiation and then put them in a circuit with uniform superposition. And that effort was basically order n square to construct all these stuff. How many gates are inside here? Well, you can count. It's not, there are n gates over here. These are all control operations, but again, number is nothing but n. You produce this particular state, which was exactly what Fourier transform produces, and now you undo the Fourier transform and you will get 5, and the 5 was the eigenvalue which you are looking for. And the point is that the effort to find is polynomial in number of bits. So that is what we gained, that here direct multiplication would have taken order capital N square work. Here you have this circuit. You produce this nice state with modular exponentiation and apply the inverse Fourier transform, which we knew how to do over here, and effort is actually n square. So the whole stuff is actually n square at this particular level. I just wrote it as a polynomial in n. That is good enough. And this is what Kitaev came up with as a solution to the problem, that yes, you can solve the phase estimation problem with Fourier transform using effort, which is just a polynomial in the number of bits. And now we will go back in the next lecture to see exactly what happens when the function is not arbitrary, but function is given by this power function, which is the function on cyclic group on which we are trying to find the period. But this works for all expressions. We have to figure out some extra features like what happens with a finite number of bits, with the precision. And so there will be determination of this phase up to some accuracy, not a complete real number with arbitrary number of digits, and it will produce some error. You can calculate how much is the error in the accuracy and estimate the effort in presence of that particular error. So those are now matter of details, but they can be worked out. The main point is this Fourier transform solved this phase estimation problem. And now if you are clever enough, you can solve this problem by filling in certain gaps. Some more features are needed, including some facts from number theory, but I will come to that next time.